Hello, everybody. I wish you all are having a good time. Uh, our research title is Numerical Investigation of Turbulent Heat Transfer Enhancement via Modified Internal Tube Profiles. The research is done by Dr. Joshua Brinkerhoff and Shahab Zeraati this year from School of Engineering, University of British Columbia, Okanagan campus. I will start with a background about the research, then I will discuss the methodology, and I will present some key results of the research, and at the end I will briefly discuss the conclusions of the research. Steam cracking is a process in which ethane is converted into light olefins such as ethylene. We have long pipes with flowing ethane and steam, uh, which are heated in a large furnace called steam cracking unit. This process is really energy consuming. The process emits approximately 200 million tons of CO2 per year worldwide. Here you can see the typical conditions of ethane steam flow. The Reynolds number is really high. It's between 55,000 to 223,000. And also the temperature is also very high. The problem that we have is that solid coke deposits form on the inside of the steam cracking pipes, resulting in fouling. So the goal is to slow this chemical formation of coke by increasing the convection, the near wall gas temperature. And if we can do that, we can decrease the process costs, we can decrease the downtime, and we can have a higher system efficiency. We want to increase the heat transfer. We have two different the heat transfer enhancement methods can be categorized into two different categories: active enhancement methods and passive enhancement methods. Active enhancement methods require external power source. For example, vibration, injection, suction, imposed magnetic and or electric force, and etc. Passive enhancement methods don't need a power source. They usually utilize special surface geometries to increase the near wall turbulent convection. For example, fins, inserts, corrugations, twisted structures, dimples, and etc. In this research, we uh, focus on passive enhancement methods. Basically, heat transfer enhancement always comes with a pressure loss penalty. We have a performance evaluation method suggested by Fan and his co-workers. This plot is suggested by them, and by evaluating the performance of a heat transfer enhancement method and showing the performance in this plot, uh, we can evaluate it. We can see if it's energy if it's energy saving or not. If the performance the performance of the heat transfer enhancement methods is in this region, in region 1, it means that it's not energy saving because the enhancement is lower than increasing pumping power. If it's in region 2, enhancement can be obtained with identical pressure drop, so it's not good enough. But if it's in region 3 and 4, we can see that that method is energy saving and is a good performance, is a good enhancement method. If it's in region 3, it means that the enhancement is still lower than increasing friction loss ratio. And if it's in region 4, it means that the enhancement is even higher than increasing frictional loss ratio. Passive heat transfer enhancement. Passive heat transfer enhancers usually operate by promoting turbulence and secondary flows close to the heated surface. We did a literature review. We reviewed different papers, different reported data, which are about increasing heat transfer in gas pipe flows by passive enhancement methods, and we evaluated their results by the evaluation method suggested by Fan and his co-workers. We saw that between different enhancement methods, ellipsoidal inward facing dimples can uh, have a very good performance for highly turbulent gas flows. Uh, they can be even in region 4. Uh, but we have some problems here. The literature lacks adequately resolved turbulence data, both temporally and spatially. So we don't have enough insight into the physical processes that yield this heat transfer enhancement. So we want to know more about the mechanisms which yields the heat transfer enhancement methods in different uh, passive and that yield heat transfer enhancement in different passive and uh, heat transfer enhancement methods. Because if we have this insight, we can design better uh, methods, more effective heat transfer augmentation methods with minimum pressure losses. Now about the methodology. We have 3 different cases here. This is the ellipsoidal inward facing dimple tube. This one is the tube with inserted wire coil, and this one is a spirally corrugated tube. We want to simulate the our flow, our turbulent flow inside these 3 uh, uh, tubes, and we want to compare their heat transfer enhancement performance. In addition to these 3, we also simulate the flow inside an unprofiled tube, a smooth-walled pipe, in order to validate our numerical method. The flow condition, the range number is 90,000 and the Mach number is 0.157. The governing equations that we have are the filtered incompressible Navier-Stokes equations, which are solved using large eddy simulations. The temperature transport is treated as a passive scalar because the increase in bulk temperature from the inlet to the outlet of all these cases is lower than 30 degrees Celsius. The subgrid stress model is wall adapting local eddy viscosity or veil, and the equations are discretized using second order finite volume method, and they are solved within open form libraries. Here you can see the grid systems that we have for these 4 cases, the unprofiled tube and the coil insert, dimple tube, and the corrugated tube. The grid resolution is followed based on the suggestions of Kravchenko and Chapman for LES simulations. Delta R plus is between 0.5 and 21. The grids are structured and they are very fine close to the wall, around 0.5. And the biggest delta R plus, which is in the core region of the pipes, is lower than 21. Delta Z, Z is the streamwise direction. Delta Z plus is around 68, and R delta theta plus is around 21. And it's ensured that at least 30 rows of cells are within R, capital R minus R plus lower than 100. Our boundary condition, we have fixed temperature and no slip condition over the pipe inner surface. We have zero gradient condition for pressure at the inlet and zero gauge pressure at the outlet. The velocity is constant, the inlet velocity is constant, and in order to simulate the fully developed flow, we have a technique, recycling technique, in which we map the velocity and temperature cyclically from the outlet to the inlet. Here you can see the results of the earlier simulation of the unprofiled tube. This is the instantaneous streamwise velocity contour, and this is the vorticity contour. You can see the turbulent behavior of the flow as here, and also these structures here, which show the turbulent behavior of the flow. The streamwise velocity profile and the temperature profile is calculated based on the results of the simulation, and it's compared with experimental data that we have and correlations that we have published, the published data that we have, and the agreement is really good. Also, the friction velocity is calculated, the friction factor and the Nusselt number are calculated, and they are compared with the experimental correlations and the experimental data that we have, and the relative error for all of them is low enough that we can be sure that our numerical method is accurate enough for predicting the behavior of the convective flow. This slide shows the instantaneous velocity field contours in our three cases. This is the dimple tube, this is the corrugated tube, and this is the coil insert case. The flow is from right to left. So we can see that boundary layer separation occurs downstream of the coil, and also we have the separation downstream of the dimples and inside the grooves in this case. And in these in these regions, we have low speed recirculation zones. The streamwise here we can see the streamwise and azimuthal components of the area average dimensionless mean velocity, which are obtained from the 4 large eddy simulations. As you can see here, the streamwise mean velocity is decreased inside the grooves in the corrugated tube. The green one is the corrugated tube. Behind the dimples, the blue one is the dimple tube, and also behind the coil in the coil insert case, the red one. So the streamwise velocity decrease within the textures. And also you can see the discontinuities here near the tips of the texture. And as you can see here, the textures mainly influence the buffer layer here and start of the log layer. This plot shows the azimuthal velocity, the azimuthal mean velocity, and it shows that the coil insert case and also the corrugated tube case, they added a azimuthal component to the velocity. So we have a rotating flow in these two cases. But for the dimple tube and the smooth pipe, clearly the azimuthal velocity is almost zeros. So spiral and coil textures generated a strong azimuthal velocity component, a swirling flow. Uh, in order to make sure that our domains are long enough to capture the longest coherent structures in the flow, we have calculated the streamwise velocity correlation function, which is defined here for all the three cases. As you can see here, for all the cases, it starts from 1 and it goes to, and it reaches 0 before 0.1. Here, this axis is L divided by capital L. Capital L is the length of the domain. So it shows that the longest structures, the longest coherent structures that we have in all the cases are smaller than 1/10 of the domain length for all the three cases. And after that, the correlation is, it oscillates around 0. And here at the end, close to the outlet, again, it reaches 1, which makes sense because, as I discussed in the boundary layer, in the boundary condition part, we map the velocity and temperature from outlet to inlet. So it makes sense that at the outlet, we have a totally correlated velocity with the inlet. So we can see that the lengths of the domains for all the three cases are long enough. Here, I can show the heat transfer enhancement performance of the three cases. They are evaluated using the fan evaluation method. You can see that the dimple case has the highest heat transfer enhancement and also the highest friction factor ratio. And it's in the region 3. The coil insert case is here. It's also in region 3, and the corrugated tube is in region 1. The coil improves heat transfer, although the pressure loss caused by it is also considerable, as you can see here. The heat transfer performance is within the lower region 3, verifying that this method is fairly energy saving for our Reynolds number. It is possible to increase the heat. You can see that the heat transfer enhancement is not very considerable. It's not very large. It's possible to increase this heat transfer enhancement by using using a coil with lower pitch or thicker wire, but definitely it comes with pressure loss penalty. So if we can do that, we will have higher friction factor ratio as well. The inward facing dimple tube show promising heat transfer enhancement effect. The heat transfer performance of this one is within upper region of upper region 3, illustrating that the method is the most energy saving method between these three simulated cases. The Nusselt number increase is around 85%, which is much higher than the other two cases. Although the pressure loss is also considerable. The pressure loss ratio is also considerable. It is possible to decrease the pressure loss and ratio by using by decreasing the depth or the density of the dimples, but definitely if we do that, we will also decrease the Nusselt number ratio. The simulation of the gas flow inside the spirally corrugated tube uh, reveals that this method cannot improve the heat transfer considerably and efficiently. As you can see, it's in region 1, and the heat transfer ratio is, the Nusselt number ratio is very low. The heat transfer performance of this case is within region 1, manifesting that using this tube for increasing heat transfer, uh, uh, increasing the heat transfer of the simulated turbulent convective flow doesn't save energy. The next slide is about the local heat transfer rate ratio. The relation is shown here. We have calculated the Nusselt number ratio, the local Nusselt number ratio for all the three cases, which are shown here. Uh, so this one is for the coil insert case. We can see that the heat transfer is maximum at the crest and minimum on the downstream side of the coil. Here, the red color shows the higher heat transfer, higher Nusselt number, and the green shows the lower Nusselt number. Also, there is a band of high heat transfer region, which we have further downstream of the coil. For the dimple tube case, you can see that the heat transfer rate is very high at the crest, and it's minimum on the downstream side. Also, a band of high heat transfer occurs down. The heat transfer enhancement method for the dimple is very high at the crest of the dimples and also surrounding of the dimples and in downstream of the dimples, and it's very low right on tail of the dimples. And for the spirally corrugated tube, we have high heat transfer rate upstream of the fins, as you can see here, these stripes, the red stripes, and it's minimum downstream of the fins where we have separated veg. You can see them by the color green. Now the question that we have is why we have these regions of high and low heat transfer rate. For example, for the coil case, we know that it's expected that heat transfer rate is high upstream of the coil at the crest of the coil due to the contact of low temperature flow and the coil in the stagnation region. But what's the reason that we have this high region downstream of the coils? Here I'm showing the ISO contours of Q criterion that we have for the coil insert, and here it's the average Q criterion ISO contours, and you can see in both of these figures that we have coherent structures and vortices generated by the coil, and they are moving with the flow, and here the structures are colored with radial velocity. You can see that the radial velocity around the coil is negative, so it's toward the core of the pipe, and then they come back and they reach the body of the pipe exactly above the region that the Nusselt number is high. So we think that, and the reason that we have this region is because of this coherent structure, these vortices, which are generated by the coil. Here, this figure shows the average Q criterion ISO contours, which are colored by this correlation. UZ is the streamwise velocity, and T is the temperature, and T prime is the fluctuating temperature, and UR is the radial velocity. If this correlation is positive, it means that it means that we are helping the increase in convection. And if it's negative, is that it means that the turbulent fluctuating motions are uh, against the increasing convection, so they are not helping it. So we can see that above the region that we have high Nusselt number, they are all red, means that these corrugate and these vortices are helping the heat transfer. So these structures are increasing the turbulent mixing and heat transfer rate. Same question we have here for the dimple tube. We know that at the crest of the dimples, the heat transfer should be high uh, because of the stagnation of the impinging flow. But why we have a high heat transfer around the dimples and downstream of them? Here I'm showing the isocontours of Q criterion, and you can see that we have strong horseshoe vortex structures which are formed around the dimples, and we also have long uh, coherent structures downstream of the dimples. You can see it here. This is the time average Q criterion isocontour, and you can see this horseshoe coherent structures and these long coherent structures downstream of the dimples. And also the correlation is calculated for them, and you can see that they are all red, which means that they are helping the heat transfer enhancement. So these structures increase the turbulent mixing and heat transfer rate, and that's why we have high Nusselt number at these regions. The next question that we have is about the corrugated tube. We expected that we should have high heat transfer upstream of the fins due to the contact of the low temperature flow and the fins in the stagnation region. But why the heat transfer enhancement in this case is so low? Here I'm showing the Q criterion with the same value, the isocontours of Q criterion with the same value as I showed for the previous cases, and you can see that they are really dispersed and very small. It shows that the vortices are much weaker in this case compared to the other two cases. And here I'm showing the average time average Q criterion isocontours, and you can see that the dominant structures are these stripes which are formed upstream of the fins. But as they are colored here by the correlation, you can see that they are not red. They are light blue and light red, which means that they are somewhere around 0. So these coherent structures cannot help in heat transfer enhancement. So the grooves cannot increase the heat transfer considerably, although they cause significant pressure loss penalty. Now I want to talk about the pressure loss. The pressure loss can be caused by either skin friction or form drag. We have defined a drag ratio. We have defined dr here, which accounts for both of these two. This is for the drag, for the form drag, and this is for the skin friction. And our calculations show that form drag is dominant in all the three cases. In these three cases, these three contours show this dr for all the three cases. For example, for the coil insert, you can see that we have high value of dr upstream of the coil, which makes sense because we have stagnation region there. For the dimple tube, we have high values of dr right on, on the crest of the dimples. We also have fairly high dr on the tail of the dimples, as you can see here, which is because of the recirculation of the flow. And for this case, for the corrugated tube, we have high values of dr upstream of the fins, again because of the stagnation point. So here it shows that, for example, for the coil, it shows that if we can somehow change the geometry of the coil in a way that we decrease this dr upstream of the coil, it can be really helpful in order to have quite the same heat transfer ratio, heat transfer enhancement ratio with a lower pressure loss. So to sum up, improving the streamlining of the textures may reduce the flow pressure losses with minimal impact on heat transfer enhancement. For the dimple case, for example, if somehow we can change the geometry in a way that we decrease the pressure loss here on the crest and on the tail of the dimples, it will be really helpful. So our future research is to change the geometry of the dimples based on the insight that we have now based on the results of this research. So we will work on vortex generators, ramps, and oblate spheres in order to decrease this pressure loss. And if we do that, we may move this performance to region 4 for the dimple. So to sum up, we did 3 largely simulations for the circular coil insert, the ellipsoidal dimples, and the corrugated tube configuration. We did that after validating our numerical method by simulating unprofiled pipe. For each of these cases, we evaluated the thermal hydraulic performance, and we analyzed the effects of the geometry on heat transfer and pressure loss. We show that inward-facing dimple tube achieves the most efficient heat transfer enhancement. It's in upper region 3. The heat transfer rate is enhanced considerably by means of generating coherent vortex structures around the dimples and downstream of them. But the pressure loss is also very high on the head and on the back of the dimples, which can be reduced by modifying the shape of the dimples. Coil insert case also yields a relatively efficient heat transfer enhancement. It's in lower region 3, although the enhancement is much lower than the dimple tube. The heat transfer enhancement is achieved by means of generating vortex structures which are shed from the coil, and they are reattached to the pipe body. The form drag caused by the coil is significant, suggesting that the modification of the coil cross-sectional shape can be helpful in order to decrease the pressure loss penalty. And the last conclusion is that the corrugated tube, for increasing the heat transfer of such a turbulent flow that we have here, such a turbulent gas flow that we have here, is not effective. The heat transfer enhancement made by the tube is neither considerable nor efficient, and the turbulence mixing in this tube is low due to the lack of effective near-wall vortex structures. And here the references are listed. Thank you all for your time, and have a great day.